So here's a problem. We want to construct the influence line again, but now we want the shear at C. You see shear is right here. So we know that we're going to have to cut the structure here at C. So which side do you want to work with, the left side or the right side? It doesn't really matter. You guys pick.
Probably, I think
left, right, left, right, left, right. It's a choice we have today, actually. Left, right, left, right, left, right. I go left. I don't know why. I just do. So if I go left, I'm going to have to find the reaction at A. I'll call it AY. So for a unit load, I'll draw it in a different color here. Let's say, here's my unit load, and it's at some distance x from the left side. So the first thing I want to do is I want to find AY. How can I find AY for a unit load at position x? Well, I have two unknowns, right? There's AY and BY. I need to do what? I need to sum moments about B. So if I sum moments about B, what do I get? Well, my unit load, what's the distance from B to the unit load? Well, I know X is from A to there, so this distance should be 12 minus X. And that'll create positive moment about B. So I'll have the force 1 times a moment arm of 12 minus X. And then I'll have AY creating negative moment. And it'll have a moment arm of, excuse me, 12. So I can solve for AY. It looks like it's just going to be all that divided by 12, which is 1 minus X over 12. Does that make sense? Basically, that's the influence line for AY. So when my unit load is at 0, that means it's right here. AY is 1. That makes sense. And as I move to the right, the value of AY decreases. In fact, when I go all the way to the right-hand side at x equal to 12, what's AY equal to? 0. So that's good. So now I can actually make my cut. So I'm going to cut my structure. There it is. And I know what AY is. What is AY? It's 1 minus X over 12 for any position of the unit load X. This is a distance of 3 feet. And I'm looking for shear at C. So here's my positive shear at C. And now the unit load, if it's here, at some distance x. So this will be the case where my unit load is somewhere between 0 and 3. So that means my unit load can be anywhere it wants between 0 and 3. So how do I find the shear at C? How do I find any vertical force? Wow, it's really quiet in here. Why is it so quiet?
Approximations test after this.
So I'll sum forces in the y direction. I don't know what you would do, but I would sum forces in the y direction. So what are my forces in the y direction? Well, I've got my shear at C is acting down. I've got this force acting up, so that'll be plus 1 minus x over 12. That's my reaction at A. And then I've got my unit load acting down. So what is the shear at C? Looks like the 1's cancel, right? And I get minus x over 12. But that's only good for the first 3 feet. So how do I get the rest of the from 3 to 12? Well, I draw the same free body. Yeah, I draw the same free body. My influence line for the reaction has not changed because it's a function of x, so it's already accounting for my position. The shear at C is still the shear at C. Of course, it's going to change value. And my little free body is still 3 feet. But now my unit load is somewhere between 3 and 12 feet, which means it's not on this free body. It's now over here somewhere. See the difference between these two? They're identical, except in the first case, from 0 to 3, it's saying the location of the unit load is there, between 0 and 3. And then when the unit load is between 3 and 12, it's not on this free body anymore. It's gone away. Elvis has left the building. That's too old a reference. Sorry about that. You can't find the Pokemon anymore. Too new a reference? Should I bookend it and go somewhere in the middle? That'll be a challenge. I'll have to think about that one. Do the same thing. Let's sum forces in the y direction. So, the force is still down. The shear at C is acting down. And this force is acting up. 1 minus x over 12. Solve for the shear at C. And I get 1 minus x over 12. All I have to do is plot these two things. So I'll do it. So remember, we're finding the shear at C. And we're going to plot that as a function of the position of the moving load, which is 3 and 12. So from 0 to 3, it's this value. So at x equals 0, what do I have? 0. At the other end, where x is equal to 3, I have negative 3 over 12, which is 1/4. See that? Now, from 3 to 12, I use this equation. So plug in 3 here, what do you get? You get 1 minus 1/4, which is 3/4. Oops. Go all the way out to 12, what do you get? 1 minus 1 is 0. So we get a linear line between these 2 points. That is the shear at C as the load moves. So if I start off here at A, what's the shear at C? 0. As I move and come up just to the left of C, what's my shear? It's 1/4 of my weight. Let's say I'm 200 pounds. So what would the shear be? Minus 50. Then I just step a fraction of anything you can imagine just to the right of C, and what does the shear jump up to be? 150 pounds, 3/4 of my weight. And it changes direction. And then it decreases linearly so that when I walk all the way down here and stop at B, what's the shear at C? 0. So imagine instead that C is some kind of connection between two beams. And it's not me walking across there, it's me, but I am a wheel on a large truck. And I weigh more than 200 pounds. And as I come onto my structure, you can see as I approach the splice, the shear is in one direction at 1/4 of my weight. And then the minute I jump past that, it jumps to 3 times that on the other side, almost instantaneously. And then decreases. So that splice joint, as you drive over it, is shearing down and then shearing up. You ever heard that when you cross onto a bridge? That that's what you're doing to that bridge. You're abusing it. So that splice joint, what do I have to worry about? Do I have to worry about this 1/4 or this 3/4? Which one is worse?
3/4.
agree. So I'm going to design that for the larger tube. And that's just one wheel. What if I had multi-wheels and multi-vehicles? You can see it can kind of get, it can add up. Luckily, these things all superimpose, so that's going to help us out. The other thing I want you to notice, and we had this is one thing where I will allow you to think about a shear force and bending moment diagram. This is the only time. I want you to look at this particular, what is that change there equal to? 1. What's the value of my force? 1. Is this a characteristic of a shear influence line as you go from the left to the right? Yes. They'll always have a change of 1. And again, I hesitate to say this, but remember in our shear diagram, the shear stepped exactly the value of the point load. Remember, it would change instantaneously as you went from one side to the other of a fixed load. So you have a similar thing here. And this little characteristic is going to help us later when we learn some shortcuts to draw these things.
Let's say if you took that point C and moved it anywhere, it would always have that 1.
Right. No matter if I moved point C to the middle of the point, okay, this shape will change, but the difference will always be 1. Also notice that this slope and that slope are the same. You'll notice they're both 1/12, 1/12. And they're similar triangles, by the way, since the slopes are the same. So you'll notice that this one is 3 times bigger than that because this length is 3 times bigger than this length. All fundamental things that we can use later to help us draw these faster. Any questions about this one? Excellent.